Welcome. This video is going to start exploring what is called reaction rates. And reaction rate is pretty much what it sounds like. It's how quickly a reaction proceeds. And by proceeds we mean, converts reactant to products. So some reactions are very fast, like burning liquid hydrogen and liquid oxygen to fuel a rocket. But others are relatively slow, like concrete hardening or your hydrogen peroxide decomposing. So often we need a quantitative value or a number so we know a little more about the reaction rate. So often what we're calculating is called the average reaction rate, which is the change in concentration of any of the reactants or products over time. So another way to express that is, like I have it at the bottom, we use the delta to represent change. So the change in a concentration of a reactant or the change in the concentration of a product over your change in time. And so the other thing that makes reaction rates a little bit unusual is you can only look at one rate at a time, so you're only using one reactant or one product. So we express the answer in a rather strange unit, moles per liter seconds, and that's because your concentration generally is going to be expressed as moles per liter, or capital M, and your time is usually going to be in seconds, or it's possible it could be moles per liter minutes if it's a slow reaction, or even hours. But so we have kind of a strange unit, and we also then include whether that's a reactant being consumed or product being produced, and we let you know which reactant or which product that is based off of. We always give it as a positive value, so even if it's a reactant being consumed and the amount is decreased, instead of expressing it as a negative, we simply say reactant consumed, or we let you know it's the reactant and you can figure out that it's being used up. A couple other things is the rate always starts quickly and then slows down over time. Even a slow reaction, the quickest the rate goes is at the beginning, and then you'll immediately see this slowing over time. And that's because fewer reactants are available. If you think about popping microwave popcorn, when you get it popping, you hear a lot of kernels popping, and then very quickly that rate starts slowing down and gets slower and slower and slower. So reaction rates are very much the same. As there's fewer kernels or fewer reactants available, that rate's going to slow down. Also, the rate will be different for different substances in the equation, so it doesn't matter which reactant or product you calculate the rate for. You just have to let people know which substance you calculate it based on, because the molar ratios then would allow us to be able to predict what the rate would be for the other substances in that reaction. And we'll see this in an example here. So for my example, I've only told you that butyl chloride reacts with water and the following data is collected. Don't have the balanced equation or even the products, but I don't need it because I'm only being asked to calculate the reaction rate based on the C4H9Cl. So remembering that rate is equal to my change in concentration, in this case C4H9Cl, over my change in time. I can take 0.220 minus 0.100. I'm just going to take big minus little, since I know my answer has to be expressed as a positive value. So it's going to be 0.120 divided by the 4 seconds. And so I come up with an answer of 0.0300. And then this is expressed as moles per liter second. And that's of C4H9Cl being consumed. So for the try it, I've given you a little more information. If Cl2 is becoming 2 Cl ions, negative ions, and at 0 minutes there's 1.2 moles per liter of Cl2, but 0 moles per liter, I'm sorry, I should have an M here, of the Cl minus, and after 3 minutes the Cl2 is down to 0.600 moles per liter, and Cl minus we don't have a measure of. I've asked you 3 questions here. First of all, what is the average rate at which Cl2 is consumed? Well, that's pretty straightforward, because I just need to take my difference in concentration, 1.20 minus 0, and divide by the change in time, which is 3 minus 0. So this is going to be 0.400 moles. And in this case, it's liter minutes. And then my second question says, what will the average rate for Cl minus be? Well, it appears like we can't do this because we're missing our second concentration for Cl minus. But actually we can do this because this is moles of Cl2 consumed per liter, moles of Cl2 per liter per minute. And so looking at my reaction, I see that I should expect to get 2 moles of Cl minus for every 1 mole of Cl2, or actually I could moles per liter, you go with the concentration here. So I can expect that my reaction rate is 0.800 moles per liter minute based on the Cl minus. And if I know that, then how much Cl minus would be produced after 3 minutes? Well, 3 minutes would be my total time involved. So I could expect 2.4 moles per liter, because my minutes will cancel out, of Cl minus. The other thing to discuss with reaction rate is what determines the reaction rate? What are some things that make a reaction faster or slower? Well, it all has to do with this idea of collision theory. And collision theory really goes back to kinetic molecular theory, which is the idea that the molecules, atoms, ions, whatever you have in your system, are constantly moving, which means they're constantly colliding. So more collisions in general gives you a faster reaction rate. But it's also important to realize most collisions between reactant particles actually do not produce the product. Why not? Because to be a successful collision, the collision needs to have enough energy and also what's called proper orientation. Orientation just means it has to hit in the right spot. If you play a sport, tennis, golf, any of these different sports that involve, striking a ball or something, oftentimes you talk about the sweet spot. You hit it just right and it really carries well. Well, that's the same thing with collision theory here, or with reaction rate. The reactants have to collide in the right place in order to be successful, and then they need enough energy to get the job done. So, 3 requirements of a successful collision. First of all, the particles have to collide. If 2 of the same reactant particles collide with each other, unless that's what's supposed to be happening, then no product is going to form. Secondly, they have to have the right energy, and we call this activation energy. It's enough energy to activate or get the reaction going. And what this really is enough energy to break the old bonds. And then third, this proper orientation, as I mentioned, means the molecules have to hit each other just right or in the right place. If you have, say for example, our butyl chloride molecule, C4H9Cl, you've got 4 carbons bonded to each other, along with 9 hydrogen and 1 chlorine. And when you react it with water, it's the chlorine bond that needs to be broken. So if the water molecule hit one of the carbon-carbon bonds or the carbon-hydrogen bond, that's not going to do anything to get your reaction going. So proper orientation means hitting the right place with that right energy. Another analogy is, think of it like throwing a dart at a dartboard. You really need 3 things to happen for your dart to stick to the dartboard. First of all, you have to throw the dart and it has to hit the target. Secondly, the sharpened end of the dart must hit the target. If your dart rotates and hits the side or the back or something, it's not going to stick. And finally, the dart must have enough energy to pierce the target. It's possible that you throw the dart, the sharp end hits it, and it still bounces off. It simply didn't have enough energy to pierce the target and stick. So here's a graphic that I pulled out of your textbook. And when you look at this, the first 2 examples up above here show 2 collisions. So we've got carbon oxygen, CO, carbon monoxide here, is on the left. And then we've got NO2 on the right. And these two are trying to collide to form CO2 and NO. So on this first example, the two oxygens hit each other. Well, that's not going to be successful. They're just going to rebound because that's not where we need the break to be. And in here, this also isn't successful because it's not hitting quite where we need it to be. Let me scroll up here. But down here in sample C, finally the collision occurs where it needs to be, between the nitrogen and one of the oxygens, between the carbon and one of the oxygens on the nitrogen dioxide. And in fact, it not only collided in the right place, but it had enough energy to stick and then form the new product. In D, you see what appears to be the same collision, but not quite as much energy, which is being symbolized by this kind of haystack looking thing. So even though it had the correct orientation, there wasn't enough energy to actually cause the reaction to happen. So need the collision, need it in the right place, the correct orientation, and need the correct energy.